Hi. So today we're gonna try to solve the Laplace equation in yet another context. So in the previous lecture, we studied the solution of the Laplace equation in in the in the cylindrical coordinate system, where the equation looks like this. Um, And then we took the limit where we allowed the z dependence of the solution, but not the angle dependence. So therefore, this derivative part was taken to zero, while this z derivative part was remained finite. And the solutions that we found there were actually quite useful for solving problems like this, where you have a cylindrical shape of a conductor, but they are at different potentials for the two halves. Okay, but this time we're gonna revisit the same Laplace equation, but however, assume a different kind of dependence. So this time we're gonna assume that there's no z dependence in the solution, but there is a dependence on the angle phi. And therefore, the equation that we'll be interested in solving this time will be looking like this. And the solutions to this problem will be useful, for example, for solving problems like this. So here is a wedge, and the unshaded region is the vacuum, and the shaded region is a conductor. So you take a piece of a conducting sheet and bend it at this angle beta, and ask what is the resulting potential and the electric field in the region in between, inside the edge, inside the wedge. So along the z direction, which is the direction out of the page, we're assuming that the conducting wedge basically extends out to infinity, and therefore there will be no z dependence in the solution. However, this angle phi should be manifested in the solution, because clearly there is an angle dependence in the geometry of the problem, and therefore there will be angle dependence in the solution of the problem as well. And furthermore, there's an obvious boundary condition at work here, which is that on the surfaces of the wedge, which are the surfaces of a conductor, you have to impose an equipotential, which we can, without any loss of generality, we can take to be a zero potential. Okay, so you solve for the potential in this region, the vacuum region, and then fix the various constants in the solution by imposing these boundary conditions that they become zero on the surface. So again, we divide up the solution into two parts. One part only depends on the radial coordinate, and the other part only depends on the angular coordinate. And by going through the familiar procedures, you will arrive at this equation. I should put the equality sign here, equal to zero. That's the equation satisfied by the angle-dependent part of the function. And the radial coordinate dependent part will satisfy such an equation. And therefore, the solutions will be either sine or cosine for the angular part, and rho to the kth power or to the minus kth power for the radial part. And one should not forget the case where k just might be 0, in which case we will have second derivative of the angle-dependent function equal to 0, and therefore the solutions will be like this. Just a linear function on the angle. And in that case, the radial part of the solution also simplified to a constant plus logarithmic function. So putting all these pieces together, we come up with the most general solution, which has this form here. And then some overall possible product forms like this. Okay, so we have a lot of constants to fix. So now it's time to try and fix these constants by looking at various boundary conditions. So first of all, this b of k is not acceptable because as you go near the origin, by origin I mean the center or the belly of the wedge. So rho of minus k, this sort of solutions will predict that the potential diverges. But that's quite unphysical, so we do not want to see that happen. And likewise, this potential log of rho that also diverges, and we don't want that either. So to prevent those things from happening, we have to take b0 and all the bk's to be 0. And therefore, now we have a much simpler solution that looks like this. But there's still a lot of constants remaining. And so we need to invoke more boundary conditions. Now let's think about what happens near the origin. By origin, the origin is specified by taking rho equal to 0. Okay, and that's good because when rho is equal to 0, this entire thing vanishes. And all we have left is just this thing, a plus b times angle. But the origin is part of the continuum of the conducting surface. So over there, we also have to have a 0 potential. And the only way to make sure that a 0 potential is satisfied is by recurring that both of these constants vanish. So now we have an even simpler form of the potential. So now this is getting kind of fun. We're incrementally approaching the true solution of the problem. Now, let's look at some more boundary conditions. Now, along this surface, the potential has to be 0. Along that surface, the potential has to be 0. And these two surfaces are characterized by the angle phi equal to 0 and the angle phi equal to beta. So let's try to take those factors into account. So when phi is 0, this entire thing has to vanish. When phi is equal to beta, this entire thing has to vanish. And the only way to ensure that happens is if we take this phase angle to be 0 for all the k's, and also require that sine of k beta to be 0 for all the k's. Now, again, we know how to make that happen. We just quantize the k values to be an integer multiple of pi over beta. And so finally, we have this simplified form of the solution of the potential, um, which is given as the sum over all possible positive integers n, and the solution has this power series form. And still, there's this unspecified constant Cn. Uh, so now to finally fix these, we need to go to a row going to infinity, right? So to fix Cn, we probably should have a look at the boundary conditions coming from this large row region. But we're not imposing any boundary conditions there. So without imposing such boundary conditions, we're no longer able to fix this remaining set of constants Cn. And the other problem is that this solution being some positive powers of rho will diverge as rho becomes very large, um, which sounds a bit unphysical, right? But the potential diverging seems to imply that the electric field will also diverge, which would imply that the electric field coming out of these conducting plates, as you go to a larger distance, the electric field will get stronger and stronger. Actually, that's true, but it's only true because we're assuming this highly artificial situation where imagine it's possible to have an infinitely long um, sheet of conducting surface. So that's a bit of unrealistic situation. That's why you find this diverging potential at large radial distance rho. So what we're going to do is to use this solution, but only apply it to the situation near the origin, where the potential does not diverge. And we say, okay, so there's a slight amount of unphysicalness in the solution we found, but it's okay because we only plan to use that solution to study the behavior of the electric field near this opening. So whatever happens at large radial distance will not bother us too much. So with that philosophy in the back of our minds, let's examine the nature of this solution that we have found. Um, and one good way of looking at that is by calculating the electric field, which of course comes from taking the gradient of the potential. And the gradient also has to be taken in the cylindrical coordinates, where the gradient operator will take on this form. So when you apply a gradient to a function like this, then you have two pieces of components, one radial and one angular, and they each look like this. You can check this by performing some differentiation. And they can be collected into this pretty nice form. But now you see there's quite a bit of simplification to this answer when you decide to focus on the region near the surface. So near the surface, the angle is either very close to zero or very close to beta. And when the angle is very close to zero or very close to beta, then this sine function will vanish, while this cosine function approaches either 1 or minus 1. Okay, in particular, when n is 1, then this cosine function will approach cosine of pi, which is minus 1. So the direction of the electric field will have been reversed. And the situation is depicted like this. Uh, and actually, that makes a lot of sense, right? Because on both surfaces, the electric fields are sort of coming out of the surface into the vacuum, and that symmetry is pretty much in line with what we would expect on common sense. Okay, so near these surface regions, we can simplify the expression of the electric field as this form. And now you notice that because you have taken a derivative, this exponent has one less power than before. So although the potential itself was convergent, uh, as rho goes to 0, now the electric field, because it has one less power, does not all have to be convergent. For example, if this value happens to be a less than 1, that is, if beta, the opening angle, should be larger than pi times n, then in fact this function diverges as you approach the origin. Okay, so obviously the only chance that will happen is if n is 1 and when beta is larger than pi. And that situation is depicted here. And now it should make a lot of sense. When beta is larger than pi, you basically have a sharp edge, like the tip of a pencil or a tip of a lightning rod. Okay, so then what this solution would predict is that when you have a sharp metallic edge, then the electric field becomes very strong there near the tip. And this is often used as the explanation why, if you erect a lightning rod on top of a building or a house, then the lightning will strike there because it naturally attracts a high electric field. And the only way, if there's a high electric field near the tip of the rod, then electrons will tend to be attracted to that region, and therefore opens up a pathway for the lightning. Lightning is nothing but a bunch of electrons that are moving through some specified path in space. So by allowing itself to be the center of a high electric field concentration, the lightning rod basically is attracting the electrons that are falling down from the sky and prevent it from hitting elsewhere on the ground. Okay, now let me switch theme slightly, but not too much. There's a pretty interesting and amusing analogy between the problems of electrostatics and the problems of diffusion. So the diffusion is a set of phenomena which is described by a diffusion equation. So this is the diffusion equation form. And here, the object in question is not the electrostatic potential, but rather n stands for the density of whatever particles that are diffusing through the medium. Okay, so n, for example, can be the density of gas particles that diffuse through empty space, or through air, or it could be the density of ink diffusing through clean water. Okay, so whatever the specific material may be, uh, all diffusion phenomena tends to satisfy this equation. However, once you have reached a steady state, by steady state I simply mean that there's no longer fluctuation of this density over time, so therefore we can take this time derivative to be zero. Then, interestingly, the diffusion equation simply becomes a Laplace equation, and this is something we have been solving all this month, all these weeks. So the and so it turns out that the analogy between electrostatics and diffusion is more than suggestive. In fact, there's a good mathematical reason why knowing the solution in one context can directly lead you to the solution in the other context. So, for example, imagine this sharp bend of material, and this material is designed in such a way that it absorbs all the gas molecules. For example, it could be the surface of some absorbing material, which is designed to absorb all the nanoparticles that can hurt our lungs in the air. So, because the properties of the materials that coat the surface is such that whenever a gas molecule hits the surface, it will get absorbed. That means the density of the gas molecule right on the surface will be zero. Okay, but this is exactly the same boundary condition we just imposed for the potential on the surface of a conductor. Wow, then we have exactly the same Laplace equation satisfied in this region outside the absorbing material. And on the surface of the absorbing material, we also have exactly the same boundary condition. And therefore, the solutions we have found over there uh, should be, without any modification, it should be directly applicable to the diffusion problem as well. I hope this will remain as a useful reminder of why studying electrostatics problem is useful, not just for the sake of electrostatics, but also possibly for the sake of studying other problems like electrostatics like for a diffusion problem, for example. Okay, thank you.